brilliant to see you. Yeah, I want to talk about kind of a small goal. I want to talk about the universe, but particularly the two great pillars of our understanding of the universe that we've built over the last century. And we're still building absolutely now. Two of those pillars that I hope you're going to contribute to building in the future. The two pillars, two things that maybe you don't learn about at school, but you'll certainly learn about at university. One pillar is called relativity, which is Einstein's great contribution to science. And the other one is something called quantum mechanics, which is a fascinating theory. It seems very strange. You may have heard of things like Schrodinger's cat. Things can be in two places at once. But actually, quantum mechanics is our theory of everything that happens in the universe other than gravity. And today, the place where we explore that in detail is the Large Hadron Collider at CERN in Geneva, the place that I work when I'm not messing around on television. So I want to give you some idea of what we're doing now at the Large Hadron Collider and what we hope to discover within the next year or two. So absolutely current cutting-edge research. But the first thing I think to say about the ambition, because I said we want to understand the universe and our two great theories of it, is to look at the sheer size of the problem. And that's one of the things that I think captured my imagination first, when I first began to get into science, when I was 5, 6, 7 years old. It was the sheer ambition of it. Because this is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, that thing up there is the constellation of Orion that you can always see in the winter sky. But I want to I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5-pence piece and held it about 25 meters away. So imagine taking a 5-pence piece and putting it 25 meters away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5-pence piece bit of sky, and took a picture. It opened its camera shutter for thousands and thousands and thousands of seconds and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have, 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object is 13.2 thousand million light years away. It was actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5-pence piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy, with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment. 30,000 million stars. Just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things. But it's enormous. So how can you... Oh, I don't want to start that yet. There we are. So how can we possibly begin to think about explaining that? You know, how do we know, first of all? How do we know it's so big? How did we find that out from this planet that we're standing on now? And how could we begin to make theories, guesses, I suppose, if you like, about where that came from, how it began, how fast light travels, all those facts that I've said to you, or all those numbers that I've given out that are our best estimate of how the universe works. It is, of course, science. And I wanted to just play you a little video of, for me, what the best definition of science, or the scientific method that I've heard, comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. But Feynman was also, I recommend that you read his books. He was a brilliant teacher, a brilliant lecturer, as well as a Nobel Prize-winning physicist. And he gave this lecture back in, I think it was the 1960s, and it's just a 1-minute definition of the scientific method.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we... Well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So I think that's a really beautiful description of what science is. It's really very simple. It's the application of common sense in many ways. What it is looking at the universe, looking at nature, guessing about how it works, seeing what the consequences of that guess are, testing those against nature, and as Feynman said, the great power of science. It doesn't matter who you are. There's no such thing as authority in science. If your guess disagrees with nature, then it's wrong, and that's all there is to it. Easy to say, but how can we possibly compare ideas about the origin and evolution of the universe with nature? Well, if you think about it, there's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, and that's to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic. It's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day. And you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way, 1 million planet Earths. It burns 600 million tons of hydrogen fuel every second into helium. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton, and even before, we looked at the light from the sun, and after Newton, we found a way of analysing it by splitting it up into its component colours. So with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern-day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red, but when you look at the light from the sun in a laboratory, and you're very careful, and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves. See, what happens is you'll know that an element is a nucleus with electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, to elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can look at the light from that galaxy. What you find, of course, is that the spectrum is the same. The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. Now, one explanation for that, of course, could be that the elements are somehow different in different parts of the universe. But it's interesting, isn't it, that they're all shifted in the same way. And actually, there turns out to be a pattern to this shift. So what's the explanation? Well, the explanation for the shift is very simple. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it stretches, it stretches, it moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle. So just qualitatively, you can say that tells us our universe is stretching. Space itself is stretching. How do you quantify that, though? Well, this is, in many ways, even more fascinating. You see, there are certain types of objects, certain types of phenomena that occur out there in the universe that we know the brightness of very accurately. Now, imagine how useful that is. If you know how bright a light is, and you put it somewhere a long way away, and then look and see how bright it looks to you, then you can work out how far away it is. It's very simple. Obviously, it gets dimmer and dimmer the further away it is from you. Now, this is a picture of one of the types of object that we know the brightness of very accurately, and it's actually this one here. And this is a beautiful picture. This is the galaxy. So this is an island, as I said, of 100,000 million, perhaps 200,000 million stars like our sun. There are perhaps 1 billion stars in the center of this galaxy, shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the 1 billion or so suns in the center and the 100 billion or so stars in the disk. Same distance away, but it's going as brightly as 1 billion suns. How could that be? One star glowing as brightly as 1 billion? Well, it's something called a supernova explosion. It's the death of a massive star, but it's actually a very interesting one. What we think that is, it's called a type 1a supernova. It's something called a white dwarf. So that's the ultimate fate of the sun. It's a star that's burnt out all its fuel and is just sitting there in space, gradually fading away. But it's a white dwarf that had a companion star orbiting around it. Now, the white dwarf, the dying star, sucks matter off the companion star until it gets too big to support itself, too massive to support itself, and then it collapses and it explodes. And we know that process very well. It was a process that was predicted, actually, from quantum mechanics, from our theory of atoms and molecules back in the 1930s. So it's a very specific process, and we can calculate precisely how brightly that explosion should be because we understand the mechanism beautifully. So we know how bright that is. We know how bright it looks because we've taken a picture of it, so we can work out how far it is away. And this is the second bit of evidence you need. So we've got two things now. We've got that you look out into the sky and you see that things are speeding away from us because you can measure the shift in the light. And we know exactly how far those things are because we can look for things like this, supernova explosions in the distant galaxies. Now, these are rare. You get on average about 1 supernova per century per galaxy. So very rare, but there are a lot of galaxies. And this is a beautiful picture, I think, again from the Hubble Space Telescope, which is a picture of galaxies along the bottom as they usually look, and along the top as they looked on a particular day or a particular week when we were looking at them when there was a supernova explosion. So you see here, there's the galaxy as it usually looks, there's a supernova explosion. Galaxy, supernova, galaxy, supernova. Supernova in hundreds of galaxies have been measured, and we've made a map of the universe. We've got the distant galaxies, we know how far away they are, we know how fast they're receding. What happens? Well, I just want to tell you about one specific supernova, but I'll tell you what happens, because it's a fascinating one. As I said, they happen very rarely. A supernova in our galaxy happen on average once every 100 years. The most famous one happened in 1054 AD. This is a picture of it today. It's called the Crab Nebula. You can see it with a small telescope in the sky. It's a beautiful cloud of expanding gas. So this is a star that's died and exploded. 1054 AD, it exploded. How do we know that? Because it was observed by Chinese astronomers, and particularly interesting, I think, and it's one place that I had the pleasure of visiting in one of my TV programs, is this place. It's called Chaco Canyon, which is in the southwestern United States, very close to the Mexican border. There was a civilization here 1,000 years ago that built structures like this, enormous castles and houses in the desert. You see the ruins. You tend to think of or I tended to think in a cliched way about the Native Americans on the plains, you know, riding horses, and you get an impression of what they're like from Western films, cowboys and Indians films. Actually, many of these civilizations were extremely sophisticated and built these giant structures that are still there in the desert. This is in New Mexico, Chaco Canyon. And these people, this is a picture of me, of course, but what's fascinating is not me, but this here, because these people saw that explosion in 1054, we strongly believe, and this is a painting of the explosion, the supernova. Now, this was 6,000 light years away, which is a star a long way away from us. But this is a drawing of the crescent moon. This is a drawing of a new star that appeared, glowing as brightly as the moon, and it's thought that this handprint points along, you see it's on an overhang of the rock, points to a place in the sky. And with modern computer simulations, you can wind the sky back to see what it would have looked like on, I think it's July 4th, 1054 AD, when the supernova happened. And you find that indeed, that supernova would have happened next to the moon in exactly that place, at that point in the sky. It would have glown as brightly, shone as brightly as the moon, and the moon was in that shape, that crescent. So it's a beautiful piece of detective work that tells us that these people, 1,000 years ago, observed a new star shining brightly in the sky for 2 weeks, the Crab supernova explosion. So when you put all that together, what do you get? Well, so we've got lots of distant galaxies, we know how far they are away, we know how fast they're receding. What we find is something called the Hubble law, and it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the centre of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble law, exactly the Hubble law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker, because the bread is all stretching. All of space is stretching at a constant rate. So you get this fascinating law, which is exactly what we observe. And I wanted to give you the number, because it's a very interesting number. I gave a lecture. I don't know if any of you know The Hitchhiker's Guide to the Galaxy. Do any of you know that? Douglas Adams? Yeah, you do. Brilliant. Very good. If you don't know it, you should read it. It's a wonderful, funny, hilarious book. In Hitchhiker's Guide to the Galaxy, there's a very famous number, which is the answer to life, to the universe and everything, and it is the number 42. It's been famous for years. Everyone who knows Douglas Adams knows the number. It does actually turn out, remarkably, the Hubble constant can be written like this: 42 miles per second per 3 million light years. What does that mean? It means that for every 3 million light years you go away from the Earth, then things, if you go 3 million light years from Earth, so let's just step 3 million light years away, then on average things will be moving away at 42 miles a second. It's pretty slow, actually. If you go 6 million light years, things will be moving away at 84 miles a second, and so on. So every 3 million light year step you take, you add another 42 miles per second to the recession velocity of things. Now, there's something else, which is actually an exercise you can do if you like doing a bit of maths, and maths, I think, is fun eventually. Not always, but eventually. What you look here is you see this is the distance, right, in miles. I've written it in miles so that I could have 42 there, but you could turn it to kilometres easily enough. So that's a distance. That's a distance, 3 million light years. You could write that down in miles or kilometres as well. It's an easy thing to do. You just type it into your calculator, you can do it. Kilometres, kilometres cancel out. So the Hubble constant is actually, the units of the Hubble constant are 1 over seconds. Right, because these go away, distance goes away with distance, you've got 1 over seconds. So that implies that maybe you could flip it over, right? You could say, well, so what if that's 1 over seconds and I flip it over, do 1 over the Hubble constant, I get a time. What's that time? Well, that time turns out to be the age of the universe. So you can do it really simply. Convert light years to miles, or convert miles to kilometres and light years to kilometres, cancel them out, flip it over, you get a number. And the number is, with the most accurate modelling we've got today, that one. You'll find that you get something that's of order 14 billion years if you do that sum. Very simple sum to do. Actually, this is the most accurate, I think it's remarkable, the most accurate determination of the age of the universe we have at the moment, 13.73 plus or minus 0.12 billion years. That's a remarkable measurement, isn't it? That's the age of our universe measured by simply looking at the light from the distant galaxies. So I encourage you to have a go at that. You can do it. It's a piece of research you can do. Get the Hubble constant, work out the age of the universe. So that's part of my talk. It's that's how the stuff that I said at the start, how we know it. We know that the universe was very hot and very dense 13.73 billion years ago because we've analysed the light from the distant galaxies. We know it's been expanding and cooling ever since. What could we possibly say, though, about the processes that built the stars and the planets and the galaxies? I've said nothing about that. We've just measured how fast it expands. Well, there's something else which is very interesting and actually goes back to some research that was done about just 100 metres away from this room, actually, across the road, at the turn of the last century, almost exactly 100 years ago, by a man called Ernest Rutherford, who, in a little laboratory which is still there over the road, if you have time, you can go and look at it after the lecture, he discovered the atomic nucleus. He was the first person to see that atoms are built of a nucleus, a small, dense nucleus with electrons going around the outside, just by doing experiments on a bench top. That was the beginning of a journey that we've gone on ever since. It's now called particle physics. And what we found is that as you go back in time, So you start here, 13.73 billion years after the Big Bang, and sweep back in time towards the Big Bang. What happens? Well, the universe shrinks, the universe gets hotter and hotter and hotter, and in the footsteps of Rutherford, we found it gets simpler and simpler and simpler. So remarkably, and we don't really know a deep reason for this other than that we've seen it experimentally, remarkably, when you go back to the first second, or the first thousandth of a second, or the first millionth of a second after the Big Bang, you find that the universe was extremely simple indeed. So our picture is that the universe has been expanding and cooling ever since it began, and getting more complicated. So things like you and me, and stars and planets and galaxies, these complicated structures that we see out there in the universe, are in a sense properties of an old and cold universe. Right? In a sense, they've crystallized out. But if you sweep back in time, the universe, well, that structure melts away as the universe gets hotter, and you find a very simple universe indeed, a universe that we can understand to a large extent. So the problem, the scientific problem in the spirit of Richard Feynman, is to do the following. We want to guess about how this structure emerged, and then we want to do experiments. But we want to do experiments back here. What we really want to do is build a time machine and sweep back to the first billionth of a second after the Big Bang or before and observe what's happening in the universe. We can't do that, unfortunately. But what we can do is recreate those conditions in a lab. The conditions of very hot, very dense, very energetic space. And this is the lab that we do that at. It's called the Large Hadron Collider at CERN in Geneva. 27 kilometers in circumference. It's the biggest scientific experiment ever attempted, the biggest scientific experiment ever built. This is in 2 countries. Most of this, at the bottom of the picture, is France. The top of it is Switzerland. That's Geneva Airport runway. If you've ever been to Geneva, you would have landed on that runway there. So that's an airport. The experiment we built dwarfs an airport. Its job is to take the nuclei of hydrogen, so the simplest element, single protons that make up the atomic nucleus of hydrogen, and accelerate them to 99.999999% the speed of light. Right, an immense number. That means, in more visualizable terms, that they go around this 27-kilometer ring 11,000 times a second. And we do that with 2 beams of protons. One we send around one way, one we send around the other way, and we collide them together. In those collisions, and by the way, we can collide up to 600 million protons together every second in the Large Hadron Collider. In every one of those collisions, we reproduce the conditions that were present less than a billionth of a second after the universe began. And we take pictures of those collisions. I just wanted to show you part of one of the great cameras that we built to take these pictures. This is the Atlas detector, parts of which were built here in Manchester when it was being constructed. So you can see the kind of insides of it. This thing is 40 meters long and 20 meters high, but it really is, in essence, a digital camera. The collisions happen somewhere in the middle of this structure, which is now full of instrumentation, things that take pictures of the collisions. And we just look and observe. So what are we looking for? Why did we build this immense machine? Well, as of today, as of now, then this is what we know of the universe. So we know today that the universe is built of just these things. These are the fundamental building blocks of the universe as of now, as the Large Hadron Collider begins to take data. Some of them may be familiar. This one may be familiar. This is the electron. So the first subatomic particle to be discovered, the first fundamental one to be discovered, the thing that goes around the atomic nucleus to make atoms. These 2 things may be slightly familiar. They're called up and down quarks. The proton is made of 2 up quarks and a down quark, and the neutron is made of 2 downs and an up. So those 2 things are the building blocks of the atomic nucleus. And that's what you need to build you and me and the Earth and the stars and planets and everything we can see in the sky, every galaxy that we can see, we think is made of just those, the up and the down quarks and the electron. This thing, called the neutrino, completes the set of these 4. It's a kind of unusual particle in a sense. You may not have heard of neutrinos. Actually, they're intimately involved in the way that the sun shines. And in fact, in the process, the sun goes through converting hydrogen into helium. It produces copious quantities of these things called neutrinos. So many, actually, that if you hold your thumbnail up now, which is about a centimetre square centimetre, there is something like 60 billion neutrinos per second going through your thumbnail from the sun. and through every square centimetre of this room. You don't feel them because they interact very weakly with normal matter, but they're there and they allow the stars to shine. So they're important, and that's all you need to make a universe as far as we can tell, just those 4 particles. For some reason that we don't understand at all, nature saw fit to make 2 carbon copies of those, as it were. Now, carbon copies you probably don't know anymore because you don't do that, you scan things in. But 2 precise copies of those 4 particles. These are identical in every way to those 4 particles, except they're heavier. So this thing is called a muon. It's the same as an electron in every way except it's heavier. This is the tau. Same as the electron and the muon in every way except they're heavier. We have no idea why nature chose to do that. They don't seem to be any use, but we've discovered them. So we have reasonably good evidence that there aren't any more. So that's one of the great mysteries in physics, actually. Why has nature chosen that pattern? You only seem to need 4 to build everything. Nature has got 12. We don't know why. That's one of the mysteries. But the other mystery, we don't know anything about that, by the way, so we don't really know how to look. We just hope that something will crop up, someone clever will come up with some kind of theory. But there is something much more specific that we're looking for, which I can demonstrate with an equation. Now, I apologize about putting an equation up. Some of you might not like equations. This one, though, is worth looking at because it's incredibly simple in many respects. This equation I'm going to put up now describes everything we know about the universe except gravity. So everything from the way atomic nuclei work, the way that atoms and molecules stick together, the way that light interacts with atoms and molecules, the radioactive decay, the way stars shine. At a fundamental level, everything we know about the universe at the start of the 21st century is in this equation. It might not look simple to you. It doesn't look simple to me very often. But if you think about it, it's rather amazing that you can write down a piece of mathematics that describes every phenomena we know of in the universe other than gravity in such a simple and beautiful way. But there is a problem with it. I'm tempted to say, can anyone see what it is? But that would be unfair, wouldn't it? The problem, actually, it's not a problem really, it's a prediction, lies in these last 2 lines. See, the first 2 lines contain symbols which represent all the particles here. So all those things are combined in these symbols, the forces of nature, electromagnetism, all those forces, the nuclear forces that stick the nucleus together, all described in the first 2 lines. The bottom 2 lines contain this symbol here, which is a Greek letter phi. And that represents a particle that is not here, right? So in other words, there's a particle in here that's predicted by our best theory of 3 of the 4 forces of nature that has not yet been discovered. It may not even exist, but it's predicted to exist. In the spirit of Richard Feynman, we have to go and look for it. And this is one of the key things the LHC does. What is it? Well, this thing is called a Higgs field. So this thing is called the Higgs particle that you may have heard of. It's a particle that's predicted to exist in order for our theory to work. So it's really, you sit down, do maths, it doesn't work, you find a way of fixing up the maths so it describes the things you can see. And the only way, or the simplest way we found of doing that is by introducing this new thing. What does it do? Well, it gives mass to everything in the universe. So if you look at your hand, it's made of subatomic particles and they have mass, they have substance, obviously. What we found about 50 years ago now is if you just write in the masses, you say electron's got a mass, we weighed it back in 1897 actually, let's just put it in our equations. Turns out that the whole thing fails, it doesn't work properly at all, it's unable to make predictions, it's wrong, you can't do it. So what was found by a scientist called Peter Higgs is that you can introduce mass in a very interesting way, a clever way, which actually gets around all these difficulties, makes the equations work. And it's really simple, actually. It's just simply this. The universe, says Peter Higgs, is full of a field called a Higgs field. So you might imagine that this room is full of something called a Higgs field. Inside your body, there's a Higgs field. Out to the most distant galaxy in the universe, there's a Higgs field. Everything has to pass through it. So all the particles in you are now passing through and talking to the Higgs field. The way it works is that if you think of a massless particle like light, so light's a stream of particles flying around the universe, they don't talk to the Higgs field. That means that they get no mass. They stay massless. They pass through the universe unimpeded. But the electrons and the quarks and everything that makes up your body, those things have to talk to the Higgs field. They interact with it. They get dragged back by it in some way. So they acquire mass. They can't pass through the universe at the speed of light. That mechanism, which is quite simple, it's almost like pulling something through a vat of treacle, is actually our best theory of how mass appears in the universe. If that's true, and it sounds a bit convoluted, but if it's true, then we have to find these things, the Higgs particles at the Large Hadron Collider. If it's not true, and it may not be, because it's only a theory, then we know that we will see the origin, the process, I suppose, which causes mass to enter the universe. That's kind of interesting in itself, because we're saying you have substance because of this mechanism. But I think the key thing to remember is that this is our theory of 3 of the 4 forces of nature. So everything that happens in the universe other than gravity at a fundamental level is represented by this theory, and we need to know that mechanism in order to make more progress. So that's what makes the LHC exciting. And the director of CERN actually said in the press a couple of weeks ago, and I think most physicists agree with him, that if the LHC continues operating as well as it is doing now, then we should have an answer to that question within 2 years, I would say. So by the time you're finishing your A-levels and thinking about going to do physics at university, then you may be getting to university and learning about how mass enters the universe because of the discoveries at the Large Hadron Collider. So it's an exciting time to be there. I want to just mention one thing, which is kind of fun, before I move on to the last bit of the talk. Occasionally, one of the things that CERN is famous for is ludicrous stories that it might destroy Switzerland, or something like that, even destroy the planet. You read it in all kinds of bits of press. It is utter drivel, and it was quite surprising for most scientists, because where did that come from? I don't know who invented the story. Maybe it was Dan Brown or something, I don't know. But what's interesting is, in the spirit of Richard Feynman, again, science is not about opinions, it's not about arguments from authority. You have to do experiments. So you might say, well, what experiment could you do to work out whether colliding particles at these energies could destroy countries or machines or even planets or universes? What could you possibly do? Well, it's interesting that nature has been doing this experiment for the whole history of the planet. This is the only graph I want to show you, but it's a graph of particles called cosmic rays hitting the Earth. Now, cosmic rays are constantly hitting the Earth. They're subatomic particles like the protons in the LHC, and they bombard the Earth with energies far in excess of anything we can generate at the Large Hadron Collider. In fact, on this graph, all these collisions here, these are measured cosmic rays smashing into the atmosphere. All of these have energies bigger than the LHC. And this is actually a plot called the logarithmic plot. So each bit goes up by a factor of 10. So those ones there have an energy, these ones have an energy 100 times those. These ones 100 times those. These ones 100 times those. So these up here, particles bombarding the Earth with energies many millions of times the energies we collide particles with at the LHC. Many more of them have hit the Earth in the history of the Earth than we'll ever collide at the LHC. And of course, the Earth is still here. So this is a beautiful demonstration. It's interesting science in itself, because we don't know where some of those very high energy particles come from in space. We don't know the mechanism that accelerates them to these immense energies. But we do know, because we measure them, that they bombard the Earth all the time. And of course, we know the Earth is still here. So there's a beautiful experiment to tell us that particle physics is a safe thing to do. Now, in the last couple of minutes, I mentioned at the start there are 2 pillars of our understanding of the universe. One of them, quantum mechanics, is what I've talked about. It's the theory of the subatomic particles, the theory of everything. And I kept saying all the time, other than gravity, other than gravity. The theory of gravity, our best theory, is Einstein's theory of general relativity. It was written down in 1915. And I wanted to just talk a couple of minutes about relativity, because it's a beautiful piece of science. And it's very sort of important at the moment, because there was a beautiful experiment done about 2 weeks ago now. The results were announced, which confirmed for the first time with very, 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 very high precision, so the highest precision confirmation we've ever had, that Einstein was not wrong Right? His theory of gravity stood the test of the most precise experiment we'd ever been able to do. And I wanted to just show you a little bit about the results of that experiment. They were reported only 2 weeks ago. It was an experiment that was actually thought of back in the 1960s. So some of these scientists have been working for their whole careers, 50 years, on getting these results out. But relativity first. There's a very beautiful and easy way of describing what it is. Here's Albert Einstein. Einstein was a genius because he thought very simply, often in pictures, about how the world works. And what fascinated him back in the early 20th century, so in 1905 or so, was a result from a Scottish physicist called James Clerk Maxwell, who predicted, although he didn't know it really at the time, but he predicted that light travels at the same speed no matter how you look at it. So it's a bit of an odd thing to predict that. Essentially, what I'm saying is if I fly to that spotlight now at the speed of light, or let's say 75% the speed of light, and go flying towards that light, the light will hit me in the face at the speed of light. Not twice the speed of light, or 1.75 times the speed of light, but the speed of light. It's a very odd thing to predict. But that came out of the theoretical physics of the 19th century, from experiments on electricity and magnetism. Einstein was the first person to take that genuinely seriously and say, what does it imply? What happens if I say nature does work like that? So no matter how I move relative to you, we all agree on the speed of light. Well, he came up with a beautiful so-called thought experiment to work that out, and I can tell you that in about a minute, and it's the heart of relativity. He thought of this thing called a light clock. So imagine that I've got a very strange kind of clock, which is just two mirrors sat there like that. And my pendulum is light bouncing between the mirrors. So we can imagine 1 tick, 2 ticks, 1 second, 2 seconds, 3 seconds. It works as a very accurate clock. But remember that we've agreed that we all agree on what the speed of light is, no matter how anyone moves around. So what happens if I get this clock, literally on this stage, and I just walk along the stage? What do you see? Right? You see the clock ticking, but because I'm moving, you see something that looks more like that, because I started off over there and I walked over here, so the light, from your perspective, bounced along like that in a triangle. What does that imply? Well, if it's really true that we both agree on the speed of light, we both think it's the same, then you see my clock run slower than I do. Why? Because the light had to travel further to make 1 tick than it did when it was standing still. So that's a prediction. It's a very strange prediction. It says that moving clocks run slow. Time slows down when you move, from your perspective, watching me move along the stage. That turns out to be right. It turns out to be true. And in fact, the factor by which it slows down, which is given by this little equation here, you can work out using Pythagoras. And the reason I show the equation is because you might just be able to see, if you know the square of the hypotenuse is equal to the sum of the squares of the other two sides, you know that, you might just be able to see that, the squares and the square roots and things in here. When you just work it out, that's the answer you get. That's fascinating because that equation is built into the satellite navigation system. So when you get into your car and you set a satellite navigation and off you go, then the satellite navigation system works basically by measuring time differences between clocks on satellites and clocks on the ground. The satellites are moving relative to the ground and they're high up, so gravity is a bit weaker. Turns out that that means time passes at a different rate. How much? Well, Einstein predicted 100 years ago that it would shift by 36,000 nanoseconds per day. A nanosecond is 1,000 millionth of a second. That doesn't sound like very much, 36,000 nanoseconds. But light travels 30 centimeters in a nanosecond. So that means that the satellite navigation system would drift by 36,000 lots of 30 centimeters in its position measurement. It's about 10 kilometers. So the satellite navigation position would change by 10 kilometers a day if you didn't take account of that, which Einstein works out in 1905 by thinking about a light clock with 2 mirrors. Beautiful bit of physics, and it found its application a century later in satellite navigation. What's that got to do with gravity and these measurements? Well, Einstein went on from thinking about moving clocks to thinking about what happens to time and space in the presence of heavy things like planets and stars. And he found, or his theoretical prediction was, that not only does movement bend space and time, but heavy things like planets and stars bend space and time as well. And he made predictions about what that means. It actually means that when you're traveling through space near a planet, you feel like you feel a force, because you're moving through bent and curved space and time. That force is gravity. It's a beautifully elegant theory. In fact, I even wrote that down. That's Einstein's theory of general relativity. The whole theory of gravity, the best theory of gravity we have, in one line. Actually, this thing here just tells you how the mass of a planet or a star is distributed, and this thing here tells you how space and time curve. That's it. That's all there is to it. And then the picture is that as things move through this curved space, they bend because they're going through a curved space, and that's what we feel as the force of gravity. About 2 weeks ago, a fascinating little experiment was completed, a thing called Gravity Probe B. It was a spacecraft that orbited around the Earth and just measured the curvature of space and time. And it did it in a very simple way using little spinning tops called gyroscopes. Just carried them around the Earth. Einstein's prediction was that as they went around the Earth, the gyroscopes would move a bit. And they would move a bit because space and time are curved. So they wouldn't quite come back to pointing in the same direction every time they went around. That movement, that little shift, was the amount that if you look at the planet Pluto, well, it's not even a planet now, it's so small, it's been demoted. If you look at Pluto from the surface of the Earth, and you look at the angular distance between the top and the bottom, so measure the angle looking at the north pole of Pluto down to the south pole of Pluto, then that's the amount of shift in these little gyroscopes. Einstein predicted it in 1915. It was measured 2 weeks ago, and the prediction was in exact accord with the measurement, as far as we could tell. So Einstein's theory has been tested utterly beautifully and precisely just in the last few weeks, and it was in complete accord with his predictions from 1915. A beautiful bit of physics. So, to finish, those are the two pillars of our understanding of the universe that we have at the moment. We have Einstein's theory, very odd theory, that space and time are bent by stars and planets, and motion slows clocks down. It works, it's technology, it's used in the satellite navigation system. And we have quantum mechanics, which describes everything else, but we're testing it again at the Large Hadron Collider. So we've developed this picture of the universe expanding and cooling over 13.7 billion years, structure emerging that eventually turned into things like stars and planets and indeed people. Is there any way that we can go back further than that? You know, experimentally, I said that we could get back to about 1/1000th of a second after the universe began with the Large Hadron Collider. Well, to finish, I just want to show you one picture, the last picture I want to show you, which is this one, which actually you might have seen in these pictures I've been showing. It's this picture here. It's a picture of the very early universe, which was taken by a satellite called WMAP. It's actually a picture of the universe as it was about 300,000 years after the Big Bang. That's the point at which the universe had expanded and cooled enough for it to become transparent to light. So before that time, before about 300,000 years, the universe was in some ways like a giant star. It was very hot, very dense, light couldn't travel through it. But at that point, the universe had expanded and cooled enough that atoms could form and light could travel through it. That light has been traveling around the universe for 13.4 billion years or so, and we can capture it and measure it. And this is a picture of that light. So this is a picture of the most ancient light you can ever see in the universe, captured by a satellite called WMAP. And it's actually a picture of the different temperature variations in that light. So essentially what you see, and what was known for many decades, was when you looked out into the night sky, you saw it glowing with a particular temperature, which was the echo of the Big Bang in a sense. The universe was once very hot, it's been cooling down, it's still got a temperature to this day, but it's very cold. But what was found just a few years ago was that if you look at it very closely, then you see that it's not all quite the same temperature. So there are red bits and yellow bits and green bits and blue bits. These are all different temperatures. Very, very tiny variations in temperature. Very hard to measure, but they've been measured. What we think those are the seeds of the galaxies. So we think that the beginnings of the formation of galaxies, which led to the formation of stars, planets, and us, are encoded in that light. The little dense ones, the little bits that are slightly higher temperature, were actually well, actually, loads, anyway, a different temperature have actually seeded the galaxies. But there's something very interesting about this, which is what I want to finish on, I think. The point is that we also have theories that tell us how those little fluctuations formed. And they're theories about how the universe behaved a millionths of a second after it began. So-called quantum fluctuations in the very early universe. So we now have theories that can take this data. We can think about events that may have happened a millionths of a second after the Big Bang, extrapolate them forward, and some of those theories fit this data very well. So I think the most remarkable thing for me about science at the turn of the 21st century is that we've not only been able to use it for technological purposes. As Rod said, we can build iPhones, we can build satellite navigation system. We have medical science, which has transformed our lives. Our life expectancy is now not 20 or 30 years, but 80 years or 90 years. It's remarkable achievements. But actually, we've also been able to tell the story of the origin and evolution of the universe to some extent. You know, we are very, very sure that we know what happened from about a millionth of a second after the Big Bang onwards. We have a very powerful picture of that. There are things that we don't know, but we have quite a strong story about how that happened. But we also have hints that we understand what may have happened a millionths of a second after the universe began. And I think to finish, that's a tremendous achievement. I showed this picture at the start. I like it a lot. It's a picture taken by Apollo 17 in 1972 on its way to the moon. It was a picture that was taken, it's one of the few pictures that was taken with Antarctica very visible, just because of where the moon was when Apollo 17 was on its journey to the moon. The Earth was tilted. And the really beautiful thing, I think, is that it's a picture of Africa. So this is the continent of Africa dominating the image. One of the few pictures of Earth where Africa is dominant. And I think it's remarkable because if you think about it, this is the Rift Valley. So this is the cradle of humanity. This is where humans came from. Our species began its journey towards Homo sapiens, the previous versions of our species, as it were, where the oldest footprints have been found over here in Tanzania. They're only just over 3 million years old. So in only 3 million years, we've gone from the first hominid footprints, the first upright footprints our ancestors left in the sands of Tanzania, to the moon and beyond, and to be able to tell a story of the origin and evolution of the universe. How have we done that? Well, it's by the scientific method. So it's a beautiful, powerful thing. It tells powerful stories. It's not only useful, it's, I think, it's part of being human to understand about origins, evolutions, and our fate. So with that, I will say thank you. I hope many of you want to carry on that journey, by the way. There are a vast number of unanswered questions that we have yet to answer. I'm sure some of you will play a part in answering those questions. But for now, thank you very much.